सो वेलकम टू द क्लास ऑफ इलेक्ट्रोमैग्नेटिज्म। तो ये क्लास मैंने इसीलिए रिकॉर्ड कर रहा हूँ क्योंकि आई कैन अंडरस्टैंड कि इंटरनेट का थोड़ा सा इशू हुआ था ड्यूरिंग द कोर्स ऑफ क्लास। तो उसमें कितना यू हैव सीन द वीडियो और कितना जितना भी मैंने हाथों से एक्सप्लेन करने की कोशिश की, आई डोंट नो हाउ मच यू आर कॉन्फिडेंट ऑन दैट. So still I'm just making this video so that you feel you feel very much confident on this chapter, and this chapter is very important from ICSE point of view as well. Just let me know इसके बाद भी अगर कुछ भी doubts रहता है तो of course tomorrow I am going and we'll take the offline classes. So let's see. Okay, so we'll start this class tomorrow offline after this concept. जितना भी मैंने अभी just few minutes back I just completed your class online sessions, तो मुझे लगा कि थोड़ा सा ऑफलाइन भी रिकॉर्डिंग वर्जन्स भी भेज देते ताकि इट हेल्प्स यू अ लॉट. सो ओके, सो विल स्टार्ट द क्लास. द नेम ऑफ दिस क्लास इज दिस इलेक्ट्रोमैग्नेटिज्म. ये बहुत ही इंपॉर्टेंट चैप्टर है फ्रॉम एग्जाम पॉइंट ऑफ व्यू एज वेल. सो इलेक्ट्रोमैग्नेटिज्म, this word actually consisting of two words. One is the electro, so which is actually representing the electric field, and दूसरा जो है that is the magnetism, or basically this is representing the magnetic field. So the ultimate motto of this chapter is to show the relationship between the electrical field with the magnetic field and the vice versa. जैसे how the first topic of this chapter is the discussions on how using the electric field we can generate the magnetic field. So we'll just discuss few points on that initially. So let's say we are just sending a current along this wire. So from this bottom we are sending a current top. Okay, now along this wire there is a current. Now just for your information, current is nothing but the flow of charged particle. This is a flow of charged particle. Now किस तरफ charged particle का move होगा and what will be the directions of the current? So if it is the positive charged particle, then along the movement of this charged particle, the current will be in the same directions. But if it is the negative, so let's say it is the flow of electron from the right side to the left side, then my current directions will be towards the opposite direction, that is from the left to the right. So if my electron is moving from right to left, my current directions will be from left to right. It's just opposite of the movement of my electron. But if it is, let's say it's a alpha is, it's a positive charged particle, is nothing but the helium nucleus. So if it is going from left to right, so my current directions will also be from the left to right directions. So that is simple. Now if there is a current, let's say along the wire there is a current from bottom to top, so how will be the magnetic field? So this is nothing but the experiment done by the Oersted. Scientist Oersted has done first experiment and he was actually studying his student and he saw that, so agar kuch if there is an electric field, if there is a current, so magnetic needle का deflections होता है around it. Okay, fine. So magnetic needle का deflections होता है around it. How was the deflection? So if this is the current from the top to bottom to top, he saw that magnetic field, magnetic needle which can actually rotate, it's free to move, showing different deflections at different positions with respect to this wire. Now if I just simply join this one, I'll get a circular path which is on the perpendicular plane with respect to the current directions. So this actually comes to the concept that if this is my electric field, this is the current direction, so magnetic field will be circular on the perpendicular plane. So how is it so? Like if it is the perpendicular plane, if it is the horizontal plane and my current direction is vertical, so this way the current is moving from the bottom to top. So this plane, this perpendicular plane is representing the magnetic field. Now there comes question, so this circular paths is actually representing the magnetic field line. So what is it? Just to remember, this is the magnetic field lines. Now when I am talking about the magnetic field lines, as you know, for the electric field line, so this is my electric field line, so it has some directions. So that means magnetic field lines also will have some directions. Now what is that? So for that we have to come to a very important rule which is called the right hand grip rule sometimes, Also we call it a right hand thumb rule. What is that? So in your book you will find it as a right hand thumb rule. So it says that if you just orient your right hand, it's not left hand, just recognize properly कि left hand use नहीं कर सकते, we have to use the right hand. So if I just hold my right hand, if I hold the right hand and this thumb is representing the current directions, if I orient my fingers in such a way that my thumb is representing the current directions, then the enclosing fingers, these enclosing fingers, can you see me? Just focus on my fingers. So enclosing fingers will represent the magnetic field line directions. So I'll just draw quickly a kind of hand. So this is my enclosing fingers, this is my right hand, and this is my thumb. So this thumb actually is representing my current direction, so this is associated with it. So you can easily can correlate. This is my thumb, so this actually represents towards the top. So my current direction is towards the top, so I have oriented my finger. So this enclosing fingers is actually representing the magnetic field line directions. So this fingertip is this side, this finger is tip this side. So you can, if you just make a whole circle, so this will be my directions of the magnetic field. Got it? So now if I just transfer it over here, so this is nothing but this. So magnetic field lines will be rotating in a anti-clockwise directions. Now it will be the beauty if you just orient your fingers also down, like if you just orient your thumb down, if the current direction is towards bottom, from top to bottom, if it's vertically down, then your encloseness of your fingers is towards the clockwise side. If you just do this experiment by your fingers, you can easily understand that this will be towards the clockwise direction, so that you can understand. So in this case it is the anti-clockwise, but here it is the clockwise. So that means by changing the current direction, you can change the magnetic field lines direction as well. So that means electric field field is generating the magnetic field, and this magnetic field is dependent on the current directions. So that is one point. Another point is that if I increase the current along this path, so let's say same I am taking a vertically up current directions. So if I increase the, let's say initially it was a 2 ampere current, instead of that if I use a 10 ampere current, what will happen? So actually the density of the magnetic field lines will increase. That means it is enhancing. In all this case it will be towards the anti-clockwise. You just orient your fingers, you can understand the enclosing fingers will represent the magnetic field line. So you got it. Now this magnetic field lines density will increase. Why? Because I have increased the current. So from electromagnetism point of view, two things are very important to make a magnetic field. Like, so current intensity, if I increase the current intensity, I can increase the magnetism first, and the second one is it depends on the current direction as well. So these two features of the current, two features of the electric field actually will create the properties of the magnetic field line. So मैग्नेटिक फील्ड लाइंस का प्रॉपर्टी क्या होगा, वो बेसिकली ये दोनों चीज पे बहुत ही डिपेंडेंट है. लाइक एक तो है करंट इंटेंसिटी क्या है, लाइक व्हाट इज द करंट अमाउंट, लाइक इट्स अ 10 एम्पियर और 100 एम्पियर और 200 एम्पियर, एंड व्हाट इज द करंट डायरेक्शन, इफ इट इज फ्रॉम bottom to top or top to bottom, it is from left to right or right to left. So depending on that, my magnetic field lines will be oriented. Perfect, you got it. Next, moving to the next concept. So till now I have used only a single wire. Now instead of that, if I use a complete loop, let's say I am using this kind of loop. So let's say I have connected my battery over here. So you know, this is the positive side. So this is the positive side, this is the negative side. So that means current is flowing like this way. Perfect. Now current is flowing like this way. Now if I just consider a vertical plane, again it's a vertical plane. So that means my loop is just look at me. So loop is going like this way, and I have a vertical plane. So vertical plane and the relation of this loop is the perpendicular. So loop is perpendicular at which is perpendicular to this horizontal plane. So I have taken one horizontal plane and जो vertical मैंने जो loop लिया that is a vertical. Now you can easily understand the cutting point. It's basically 90 degree because vertically जा रहा है, right? यहाँ पे भी this is 90 degree. Okay. Now when how will be the question is how will we draw the magnetic field lines in this concept. So just if I just go back to the previous concept, so पहले क्या था, पहले हम लोग we have just used only a single current direction, ठीक है. तो तब मैंने देखा था कि it will be एंटी क्लॉकवाइज मैग्नेटिक फील्ड लाइंस ऐसे एंटी क्लॉकवाइज बनेगा बिकॉज यूजिंग दिस राइट हैंड थंब, दैट वाज वेरी इजी. नाउ इंस्टेड ऑफ दैट आई एम यूजिंग अ लूप. अभी क्या है, इफ यू जस्ट थिंक अबाउट टू पोर्शंस, दिस इज वन पोर्शन एंड दिस इज अनदर पोर्शन. सो हियर आई हैव वन वायर, यू जस्ट फॉरगेट अबाउट दिस वन. तो यहाँ पे तो सिंगल वायर जा रहा है ना, सिंगल वायर जा रहा है. तो उसके बेसिस पे यहाँ पे इफ यू जस्ट अप्लाई राइट हैंड थंब रूल, सो ये ऊपर जा रहा है, सो दिस करंट डायरेक्शन इज from bottom to top ऐसे जा रहा है. So your enclosing figure is again creating the how it is creating a anti-clockwise magnetic field. So it is creating a anti-clockwise, it is creating a anti-clockwise magnetic field. Now यहाँ पे क्या हो रहा है, it is going down, so it's in a similar to this current directions. Here if you just think about this portion, so forget about this portion right now. If you just concentrate on this portion, यहाँ पे करंट वर्टिकली नीचे जा रहा है. जब वर्टिकली नीचे जाएगा, जस्ट ओरिएंट योर अगेन राइट हैंड, डोंट यूज योर लेफ्ट हैंड. सो इफ यू जस्ट यूज योर राइट हैंड, देन कैसे जा रहे हैं इनक्लोजिंग फिगर्स, क्लॉकवाइज मोशन. यू आर राइट, क्लॉकवाइज मोशंस दिखा रहा है. ये बेसिकली मैग्नेटिक फील्ड्स विल मेक अ क्लॉकवाइज फील्ड लाइंस. सो इफ आई ड्रॉ ओवर हियर, सो इट इज showing a clockwise. Okay, now if I just draw this kind of magnetic field lines, यहाँ पे भी मैं ड्रॉ कर लूंगा, तो क्या हो जाएगा, यहाँ पे ऐसे जा रहा है और यहाँ पे ऐसे जा रहा है. सो यू कैन अंडरस्टैंड इफ आई कीप ऑन बार मैग्नेट, जस्ट इन बिटवीन देम, you know bar magnet. What is bar magnet? Bar magnet is just like a bar. It has one north pole, it has one south pole. And how the magnetic field lines is oriented? Magnetic field lines is oriented like this way, जहाँ पे north से start होता है magnetic fields, and when it goes towards the south. So that's how the magnetic field lines are oriented for a bar magnet. ठीक है. ओके, चलो. तो अगर मैं बार मैग्नेट यहाँ पे रखता हूँ, so now you decide what will be the north. Simple, right? It will be the north, this will be the south. क्यों? देखो मैग्नेटिक फील्ड लाइंस कैसे जा रहे हैं, यहाँ से मैग्नेटिक फील्ड लाइंस कैसे आ रहे हैं. सो जस्ट थिंक अबाउट टू मैग्नेटिक फील्ड लाइंस ओवर हियर, you can understand कैसे मैग्नेटिक फील्ड लाइंस जा रहा है. So it's also matching with my bar magnets concept. So that's how actually Oersted ने जो एक्सपेरिमेंट किया था, like putting, so the first thing what I discussed कि अगर ये वायर जा रहा है उसके अराउंड जो भी मैग्नेटिक फील्ड लाइंस है उसके बराबर मैं अगर बार मैग्नेट रख देता हूँ, तो that will actually represent the magnetic field lines, nothing but the magnetic field lines. If I join these circles, these points of this, just join the bar magnets positions, it will nothing but represent the magnetic field lines. So you can understand magnetic field lines जब भी there is a electric field. If there is an electric field and if I take one magnetic needle which can move freely, it will deflect in such a way that it orients itself with respect to the magnetic field lines created by this electric field. Got it? So फिर से एक एग्जांपल लेते हैं. जैसे मान लो कि यहाँ पे ऐसे from left to right current move हो रहा है. Now if I just apply my right hand thumb rule, how is it? So okay, you understand. ऐसे मेरा magnetic field lines will be oriented, right? This will be my magnetic field lines concept because देखो ऐसे जा रहा है, enclosing हो रहा है, right? So ऐसे मेरा magnetic field lines will be. Now अगर मैं एक बार मैग्नेट को इस तरफ रख देता हूँ, तो कैसे डिफ्लेक्ट होगा? हाउ इट विल बी डिफ्लेक्टेड डिपेंडिंग ऑन द लाइक किस पोजीशंस में इसका नॉर्थ बन रहा है, किस पोजीशंस में साउथ बन रहा है, उसके बेसिस पे। जैसे यहाँ पे मैं अगर रख देता हूँ, सो इट विल ओरिएंट लाइक दिस पे, दिस विल बी द नॉर्थ बिकॉज मेरा नॉट, दिस विल नॉट बी द नॉर्थ, दिस विल बी द नॉर्थ एंड दिस विल बी द साउथ बिकॉज मेरा मैग्नेटिक फील्ड लाइंस ऐसे जा रहा है, लेट्स से ऐसे जा रहा है काइंड ऑफ। So it has to be parallel to the bar magnet's magnetic field lines as well. So always एक इलेक्ट्रिक फील्ड के आसपास अगर मैग्नेटिक फील्ड लाइन इलेक्ट्रिक फील्ड के पास में अगर एक बार मैग्नेट रखा जाता है, सो दैट विल डेफिनेटली क्रिएट अ मैग्नेटिक फील्ड, क्योंकि इलेक्ट्रिक फील्ड जो मैग्नेटिक फील्ड क्रिएट कर रहा है उसके वजह से ये रिपल्शंस फील होगा उस बार मैग्नेट पे। एंड बार मैग्नेट ऑलवेज वांट टू align itself with the induced magnetic field lines. Okay, perfect, you got it. Perfect. Now we'll go to the next one. So I think the Oersted concept is very much clear to you. Now I'll go to the next concept, which is called the this is called a magnetism, right? Like we are already discussing about the magnetic field. Now what? So इसके बाद एक्चुअली आईसीएसई बुक में वो सोलिनॉइड डिस्कस किया था, बट बिफोर दैट आई वांट टू डिस्कस अ स्मॉल पॉइंट सो दैट इट बिकम्स वेरी क्लियर कि जो नेचुरल मैग्नेट्स होता है एंड जो इलेक्ट्रोमैग्नेट्स होता है उन दोनों के बीच में डिफरेंसेस क्या होता है। सो देयर इज वन थिंग दैट इज द नेचुरल मैग्नेट, एक तो है नेचुरल मैग्नेट्स। सो यू कैन अंडरस्टैंड जो नेचुरल मैग्नेट्स होता है उसका नेचुरल प्रॉपर्टी होता है मैग्नेटिक, तो मैग्नेटिक प्रॉपर्टी होने की वजह से इट अट्रैक्ट्स द फेरोमैग्नेटिक एलिमेंट्स। नाउ फेरोमैग्नेटिक, ये जो वर्ड मैंने यूज किया, व्हाट इज द मीनिंग ऑफ दैट? फेरोमैग्नेटिक मटेरियल। इसके एग्जांपल क्या है? बढ़िया बढ़िया एग्जांपल है, आयरन है, स्टील है, ठीक है ना। चलो, फेरोमैग्नेटिक मटेरियल, आयरन एंड स्टील। तो ये फेरोमैग्नेटिक मटेरियल इज अट्रैक्टेड बाय द नेचुरल मैग्नेट्स। तो नेचुरल मैग्नेट्स तो नेचुरल है, उसका तो नेचुरल मैग्नेटिक प्रॉपर्टी भी है, दैट वी कैन अंडरस्टैंड। तो उसको अभी फिलहाल के लिए दैट इज नॉट द पार्ट ऑफ आवर चैप्टर एंड दैट इज नॉट द पार्ट ऑफ डिस्कशन। एक है हम लोग इंड्यूस कर सकते हैं, इंड्यूस्ड मैग्नेट इसको कहते हैं। एंड ये इंड्यूस्ड मैग्नेट किससे फॉर्म हो सकता है? फेरोमैग्नेटिक मटेरियल से फॉर्म हो सकता है। तो इंड्यूस का मतलब ये है कि वी कैन इंड्यूस द मैग्नेटिज्म, वी कैन इनिशिएट, वी कैन एक्चुअली जनरेट द मैग्नेटिज्म प्रॉपर्टी विद इन दैट मटेरियल। एंड उसके लिए फेरोमैग्नेटिक मटेरियल होना बहुत जरूरी है। क्यों? क्योंकि उसका जो एलिमेंट, उसका जो एटम्स रहता है, दैट वर्क्स एज अ टाइनी मैग्नेट्स, एंड वो मैग्नेट्स एक्चुअली ओरिएंट होके एक नॉर्थ बना देता है, एक साउथ बना देता है, एंड दैट बिकम्स अ इंड्यूस्ड मैग्नेट। उसका बनाने का भी प्रोसेस है, दैट्स नॉट पार्ट ऑफ द सिलेबस, जस्ट फॉर योर इंफॉर्मेशन कि अगर मैं ऐसे एक बार मैग्नेट को कंटिन्यूअसली ऐसे मूव करूं एक फेरोमैग्नेटिक मटेरियल के ऊपर, तो ऑफ कोर्स इसका समहाउ यहाँ पे नॉर्थ है, यहाँ पे साउथ बन जाएगा, बिकॉज बाय रोटेटिंग, बट दिस रोटेशन हैज टू बी वेरी क्लियर एंड यूनिफॉर्म। लाइक ऐसे नहीं कि कर सकते जिगजैग मोशंस हम लोग नहीं दे सकते। अगर इसको प्रॉपरली मूव करेंगे तब जाके ये एक्चुअली क्रिएट करेगा इंड्यूस्ड मैग्नेट। तो तब जाके एक्चुअली इसका जो एटम्स है ना, ये टाइनी एटम्स, दिस विल बी ओरिएंटेड एंड दैट विल क्रिएट अ बार मैग्नेट। परफेक्ट। ओके, सो ये आयरन के लिए भी हो सकता है, स्टील के लिए हो सकता है। नाउ आयरन बेसिकली कहा जाता है सॉफ्ट फेरोमैग्नेटिक मटेरियल एंड दिस इज कॉल्ड द हार्ड फेरोमैग्नेटिक मटेरियल। तो दोनों के बीच में डिफरेंस क्या है? बेसिकली ये जो फेरोमैग्नेटिक मटेरियल है, इनको हमने इंड्यूस्ड मैग्नेट्स बना सकते हैं। लाइक वी कैन इंड्यूस द मैग्नेटिक प्रॉपर्टी विद इन इट, बट सम ऑफ द फेरोमैग्नेटिक मटेरियल्स आर सॉफ्ट एंड सम ऑफ देम आर हार्ड। दिस इज कॉल्ड सॉफ्ट बिकॉज इट कैन easily magnetized and demagnetized। तो इसको इजीली मैग्नेटाइज भी कर सकते हैं, लाइक उसमें इंड्यूस भी कर सकते हैं मैग्नेटिक प्रॉपर्टी, और उसको डीमैग्नेटाइज भी कर सकते हैं। और डीमैग्नेटाइज का जनरली प्रोसेस क्या होता है? एक हो सकता है हीटिंग, एक हो सकता है हैमरिंग। सो व्हाट वी आर डूइंग बेसिकली, एक्चुअली we are disorganizing again these tiny atoms, these tiny magnets. Each and every atom here works as a tiny magnet. So that's how it actually disorganizes, and that's how the magnetic property is, like magnetic property चला जाता है, and that we call a demagnetization. तो इसको easily कर सकते हैं, that's why iron is called a soft ferromagnetic material. बट जो स्टील होता है ये हार्ड होता है. हार्ड फेरोमैग्नेटिक मटेरियल का मतलब ये होता है दिस cannot be easily magnetized और डिमैग्नेटाइज्ड. लाइक इसको मैग्नेटाइज्ड एंड डिमैग्नेटाइज्ड करने में थोड़ा सा टाइम लगता है, ठीक है, एंड इट नीड्स मोर एफर्ट to magnetize as well as demagnetize. Okay, I think the induced magnets concept is clear now. So these questions questions comes generally water magnetic material. This is not only the part of the syllabus, but rest of the things is part of the syllabus, how we can, so how can we distinguish between soft ferromagnetic material and hard ferromagnetic material, and give some examples of ferromagnetic materials, and how we can induce the magnets. So these questions may come, but you should know before going to the electromagnets concept. Now another is called the electromagnets. So from the name itself you can understand, from the name itself it is the from the name itself you can understand that electromagnets is using the electrical field. It's using the electric field to induce the magnetism within that. So these electromagnets we are basically discussing. So what was the experiment of the Oersted? That was the pioneer work of the electromagnetism. Okay, so coming to the main channel, like we are discussing that if there is a loop, that will create the magnetic field around it perpendicular at the perpendicular plane. Now if I just want to create a cylindrical coil, if I create a cylindrical coil, then it will act as a electromagnet. Anywhere will act as electromagnet, because there will be some north side, there will be some south side. If I use this kind of cylindrical coil, so it's in coil but it's cylindrical in shape, you can understand it's cylindrical in shape. So if I use this coil and if I just connect it with the battery, so there will be a current flow and it will act as a magnet. Now I have already shown you, like this is, if this is north, this is south of a bar magnet, then the magnetic field lines move like this way. So it emits from north and it enters into the south. That's how the magnetic field lines will move. For the cylindrical coil as well, it will exactly work as a bar magnet, and that's how the magnetic field lines will move. Magnetic field lines will move like this way. If it is north, if it is south, then this will be the magnetic field lines directions. Okay. Now how to understand which one will be the north? So if I am giving you that this is the north side, this is the south side, it's very easy to draw. Like this we just replicate the bar magnets concept here, and we can easily understand how the field lines will be oriented. Now how to understand which one will be north side, which one will be south side? So that is most critical, another critical thing to discuss. Now the thing is, when there is a coil, so if you just look at the coil, let's say this is the coil, this is a cylindrical coil. Now if I look at perpendicularly of that coil, then definitely I can see the rotation. Is it going clockwise or is it going anti-clockwise? How the rotations will be of a coil, that will decide how my current is passing on, right? Now if it is a clockwise, if it seems that it's a clockwise coil, then it will create south pole. So if I draw S, and if I just draw two arrows at tip of the S, it will represent a clockwise directions. So that means if the coil end is representing a clockwise rotation, that will represent the south directions. And if it is for, like, if the clock's end is representing the anti-clockwise one, then it's nothing but the M, that is north. So if you just draw two arrows at the end of N, the letter M, it will represent the anti-clockwise. So I can just write, if it is the clockwise, it is the south end, and if it is anti-clockwise, it's the north end. Perfect. So now here, as I have told you, north, and here south. So can you understand? If you just see it vertically, you will able to see anti-clockwise rotations of this coil over here and clockwise rotations over here, at this south end and this north end. Now once you get the north end and south end, then you can easily draw the magnetic field lines. It's very easy to draw the magnetic field lines, that how this will be oriented. This will be oriented like this way. Okay, now I'll just introduce a single concept. Till now we have discussed in the class, but I'll just introduce one single concept so that you can also study and we can discuss it tomorrow. That is the concept of, so I'll just mention one more thing. This cylindrical coil, we call it a solenoid. Just need to remember, this is called a solenoid. Perfect. This is called a solenoid. Whatever we have discussed, this is the concept of solenoid. Now if I use one, so how we can increase a solenoid's magnetic field? If I ask you how we can increase the magnetic field line, so again from the concept of that previous one in the Oersted experiment, we can increase the current. If I increase the current, magnetic fields will increase, isn't it? I am writing in short, you have to write it in proper way. So one, by increasing the current, we can increase the magnetic field. The second one is, if I increase the turns of coil. So that means this coil, let's say this is the coil having a length of 1 meter, and within 1 meter length itself I have made this coil which is having more turn. The length is same, 1 meter. So within 1 meter it is having more turn than this. So the magnetic field lines will be more over here and it will be less compared to this because it has more turns. So you can understand, if I just use a single loop, so I have told you, if I use a single loop, instead of that if I use multiple loops, so that will each and everywhere will create the magnetic field lines. Each and everywhere will create the magnetic field lines. So that means if I enhance the number of turns, that will actually increase the magnetic field lines. You can also see from here. So that is why within this 1 meter it is having more turns. That's why as I have increased the number of turns, the magnetic field will increase. So these are the ways which we can apply to increase the magnetic field strength of a solenoid. What we are discussing about the solenoid. ठीक है. So एक तो है करंट बढ़ा सकते हैं, करंट बढ़ा के उसका मैग्नेटिक प्रॉपर्टी बढ़ा सकते हैं. एक है टर्न्स बढ़ा के उसका नंबर ऑफ टर्न्स बढ़ा के उसका मैग्नेटिक फील्ड लाइंस बढ़ा सकते हैं. थर्ड पॉइंट इज, एक सोलिनॉइड का अंदर खोखला होता है. इट्स अ hollow one, right? I have already drawn it. If I draw it again, so if this is the solenoid, this is a solenoid complete picture. So this part is completely hollow. So it's like a spring. Now if I introduce one bar of ferromagnetic material, again this is most important. If I introduce one bar, ऐसा नहीं कि मैंने प्लास्टिक बार को इंट्रोड्यूस कर दिया तो this will enhance the magnetic field. No, it will not be. It has to be a ferromagnetic material. What? It has to be a ferromagnetic material. And which one we use generally? Is it soft or hard? We use the soft. I will discuss tomorrow why we use soft magnetic ferromagnetic material inside the solenoid core, as a solenoid core. So if we using solenoid core, can increase the magnetic field. So these are the ways through which we can increase the magnetic field line. So instead, like here, which type of material we are using in the code that actually enhance the magnetic field, instead of let's say some material which doesn't have the magnetic, like the induced magnetic properties so much. So if I use those material as a core of a solenoid, it cannot enhance the magnetic field so much. Instead of that, if I use a iron, which is a soft ferromagnetic material, it will enhance the magnetic field a lot. So that's how we can increase the solenoid. Now one more point, why we should use a bar, why should we use a core, solenoid core, to enhance the magnetic field. So you have understood these concepts. Now I'm just discussing the last one concept, why solenoid's magnetic field increases if I use a solenoid core. Because this solenoid is itself creating a magnetic field. You have already seen it, right? This is creating a magnetic field. This was creating a magnetic field, let's say. Perfect. Now I am using another soft ferromagnetic, and when I am using a ferromagnetic material, it is also getting induced and it is also creating its own magnetic field. Now when there is an addition of another magnetic field lines to this solenoid's magnetic field lines, what will be the result? Magnetic field lines will increase. The density of magnetic field lines is increasing, and that's how the magnetic field strength is increasing. So that is the reason, if I use a solenoid core and if you use the ferromagnetic material inside the solenoid, it will enhance the magnetic field. So that is what today's class. If just let me know, you just go through these lectures. You just let me know if there is any kind of question. Just let me know tomorrow, and we'll discuss the rest of the part of the as far as I can complete for this chapter electromagnets. Okay, thank you. Bye bye.